Okay, so now we come to Chapter 8. Chapter 8 talks about how to summarize data. So our learning objective is to understand how best to summarize data. So we're going to start with graphical data summaries. So we can summarize data both graphically or using numbers. For graphs, we will examine the stem and leaf display, bar chart, histogram, and box plot. So the stem and leaf display is using a sorted list of numbers. So we're going to illustrate this for 2-digit numbers, although we can easily expand that. So for 2-digit numbers, the tens digit is what we call the stem, and the ones digit is what we call the leaf. So this enables us to illustrate the data frequencies in terms of the row length without losing sight of the underlying data. So stem and leaf can be used for any number of digits, but it's simplest with 2 digits. We need to divide up the digit into those used for the stem and those used for the leaves. And we can scale the numbers and note the scale below. For example, if we had 1 decimal place, we could multiply by 10 so that the numbers are integers. So this is easy to do by hand with a paper and pencil. So if you were out in the field collecting data and you didn't have your computer with you, or your phone was running short of battery life, you don't need to use a phone or a computer. You can just use paper and pencil. So we're going to start with an example where we've collected data on the size in centimeters of 10 objects, and these are 2-digit numbers. So our list is 14, 12, 16, 24, 20, 40, 42, 46, 49, and 46. So you can see that the tens digits we have there are 1, 2, and 4. Now we need to include 3 in that set, because even though we have no leaves for the 3s, right? So the 4 possible stems are then 1, 2, 3, and 4. And then if we look at the leaves, so for the stem of 1, you will see we have 14, 12, and 16. We're going to sort the leaves. So not only do we sort the stems, we also sort the leaves, and we include all duplicates. So the 3 leaves we have are 4, 2, and 6. We sort those, that's 2, 4, and 6. So that's why you can see at the bottom of the page, for the stem of 1, we have leaves of 2, 4, and 6. If we look at the stem of 2, you can see we have 24 and 20. So that means the leaves in sorted are 0 and 4. For the stem of 3, we have no leaves at all, but we need to include it so we can see that there is a gap in our data. And then for the stem of 4, you will see we have 0, 2, 6, 9, 6 as the leaves. After sorting, that becomes 0, 2, 6, 6, 9. So you'll notice that there is a duplicate 6. There are 2 46s, and we need to show both of those so we can actually show that we did have a duplicate 6. Now, when we look at this, you can see that there is an apparent gap in the middle of our data. So it looks like we may really have data that can be separated into 2 groups. One group of data that runs from 12 to 24, and then a gap between 24 and 40, and then another group of data from 40 to 49. Okay, so if we were out in the field like this would immediately beg the question, is there some way we can discriminate between those 2 sets of data? Are they different types of objects? Or is there some other reason why we apparently have 2 populations rather than 1? So, just to remind you, stems and leaves must be sorted. We must include duplicates, and stems with no leaves must be included. Now we can make variations. So for example, we can split the stems into 2 stems if the number of stems is too small. So we could put leaves 0 to 4 on one stem and 5 to 9 on another. So the previous plot would become something like this. So we would, for the stem of 1, we would have 2 to 4 on the first stem and 6 on the second. For the stems of 2, we only have a 0 and a 4. We have nothing from 5 to 9. We have nothing on either of the two stems with a 3. And for the stems with 4, we have 0 and 2 in the leaves 0 to 4, and 6, 6, and 9 in the stems of 5 to 9. So now you can see even more clearly that there is quite a large gap in the middle of this data set. Okay? So this gives us, stem and leaf is quite nice because we have all the information, at least to a 2-digit level of accuracy. We have all the data being there. We haven't lost any of the information at all. And we can see very clearly what the pattern is across the values. Now, in fact, a stem and leaf can be seen as essentially a form of a bar chart or a histogram. So a bar chart is a chart where the height of the bars is proportional to frequency, or if we want to make it like this, a horizontal bar chart would have that the length of the bars is proportional to frequency. So you can see the stem and leaf is in effect a horizontal bar chart. It's also essentially a histogram. So what's the difference between a bar chart and a histogram? So when you do a chart in Excel, it gives you the option of a bar chart. It doesn't mention histogram as such. A bar chart, the difference is that the area of the bar is proportional to frequency. So not the height of the bar, but the area. Now, of course, if all the bars have the same width, then the area of the bar is proportional to the height of the bar. So that means a bar chart and a histogram are equivalent if we have equal widths. But if you merge some of the groups, then clearly there will be a difference between a histogram and a bar chart. So from a statistical point of view, a bar chart is what we want. We want the area of the bar proportional to the frequency. So for example, this same data set, if we now choose a bar chart or a histogram, this is what we get. So you can see that other than rotating it 90 degrees, this looks very similar to what we got from the stem and leaf. Again, we can see there is a gap in the middle. And then but here we have lost sight of the original numbers. So in some ways that may appear better because we can see the graphic without being distracted by the digits. But the disadvantage is we've lost the original digit. So we can't see if there is any pattern in the digit. So in fact, if you go back to the stem and leaf plot, do you notice anything odd about the digits in the leaves? Okay, can you see anything odd? You should notice that we have 0, 2, 4, 6, and 9, but we don't have any 1, 3, 5, 7, or 8. Right? So that in itself is a little bit odd. Why do we only have certain digits? That might make us suspect that there is some pattern in the way the measurements have been taken. Maybe some grouping has taken place which we cannot see. Right? Okay, so that's the bar chart or a histogram. It's both a bar chart and a histogram here. The next option we're going to introduce is what's called a box plot. So a box plot, we have a box that shows the central half of the data with a line showing the middle, and the whiskers, which are the lines coming out the edge, and the dots are showing more extreme data. So it's perhaps not obvious what this all means. So the line in the middle of the box here tells us that half of the data is less than that value and half the data is more than that value. And then the two vertical lines at the end are the minimum and the maximum. So let's just go back and have a look here. You'll see the smallest value, the minimum was 12 and the maximum was 49. So that's the vertical lines on the left and the right. What we can't quite see so obviously is that the vertical line in the middle you can see is at about 32. So where does the 32 come from? So where is the middle of our data set? So you will see that we have 5 data points in the lower part and 5 data points in the upper part. So the midpoint is clearly somewhere in between 24 and 40. So in fact, the midpoint of 24 and 40 is actually 32. So 32 essentially is the point that divides our data set into two, where we have half the data values below 32 and half the data values above 32. So as we'll see in a minute, this is something we call the median. So what about these other two vertical lines around the box? So it turns out that these other two vertical lines, which are the beginning and the end of the box, divide up the data into quarters, right? So we haven't yet dealt with this. This is something we call quartiles. So in fact, these 5 vertical lines here divide up our data set into 4 parts with equal amounts of data. Now this box plot looks very odd because you'll see that the central box is very wide. It's almost as wide as the full range of the data. Why is that? And that's because we have this big gap in the middle of our data set that we can see in the stem and leaf plot. So the box plot is in some ways doesn't represent this data set very well, in that we can't see the gap in the middle of the data, which we can see in the stem and leaf plot or in the bar chart or the histogram. Okay, so now we come on to numerical summaries for our distribution. So we're going to start with numerical summaries for the center of our distribution. So first of all, the one which I'm sure you're all familiar with, the mean. The mean is just the average value, meaning we add all the values up and divide by the number of values. So we often use the Greek symbol mu for the population mean. We often write the sample mean as an X with a bar above it. And we often write the formula for the sample mean as sigma xi over n. So that sigma sign means we add up all the x values, and n here is our summary for the sample size. So for the sample mean, we just add up all those values. If you add up all those values in our previous data set, they add up to 309. We had 10 data points, so the mean is 30.9. But we don't need to do this by hand. We're generally going to get the computer to do it for us. It's much less likely to make a mistake as long as we've accurately input all the data values. So the second possible summary is what we call the median. So this was the line in the box on the box plot. The values such that half the values are less and half the values are more. So if n is the sample size and is an odd number, then the median is just the n plus 1 over 2th biggest or smallest value. So if we had 5 values, 5 plus 1 is 6, 6 over 2 is 3. So the third biggest value out of 5 or the third smallest value out of 5 should both be the median. But if n is an even number of values, such as in our example just now, it's not so obvious what's the middle value. So what we usually use is the average of the two middle values. So the n over 2th and the n over 2 plus first values. So in our case, n was 10. So it's the average of the 5th and the 6th value. So we can either count up or count down. And we can easily read it off the stem and leaf plot because our values are already sorted. So if we go back to our stem and leaf plot, if we're going up, the 5th value is 24 and the 6th value is 40. We need to be a little bit careful about the ordering of the leaves. So the average of 24 and 40, I already said, is 32. Similarly, if we're reading down, the 5th value from the top is 40 and the 6th is 24. So again, the average is 32. So it's relatively easy to calculate the median, particularly if we've already done a stem and leaf plot, so our values are already sorted. The third way we can summarize the center of the distribution is the most common value, which is called the mode. So do we have a mode in this data set? We actually do. We have one value which occurred twice, which is 46. But you'll notice that the mode may not be unique in some data sets. So if, for example, all 10 of our values were different, then all values of the data set would be the mode. They would all be equally likely. So the mode has a problem that it may not be uniquely defined. There may be multiple possible values for the mode. So let's compare the mean, median, and mode to think about when we might use each of these. So the mode, as I said, is not always unique. It's not what we call robust, meaning changing one data value slightly can cause a large change in the mode. So we don't usually use the mode. The only reason you would ever use the mode these days is because your data set is so enormous and it's the quick way to summarize the data in terms of the center. But usually we can afford to do the calculation for the mean or the median. So it turns out that the mean is easier to deal with mathematically, and we will see why that is later. So most theory in statistics is based on using the mean, but the median is more robust. So robust means in the everyday sense of the word reliable, it's more reliable in that it's not as easily varied if there are some errors in our data. And we'll illustrate that in a minute. So in our example, we already said that the mean was 30.9, the median was 32, and the mode was 46. So what would happen if accidentally we input one of those values wrong? So if when we're inputting the data, so let's go back and look at our data again. Let's say that when I was inputting the 49, I meant to type 49.0, but I accidentally typed 4900. So it became 4,900 instead of 49. So what would happen if we changed that largest value of 49 by a factor of 100? Well, the median wouldn't change. 32 would still be the center of our distribution if we look at in terms of dividing the distribution into two. The mode would not change. It would be 46 in this case, but the mean would jump all the way up to 75. And in fact, in this case, the mean would be bigger than all the values except for that largest one. So you can see that the mean changes substantially, but the median does not change at all. So that's what we mean by saying the median is more robust. It's not as easily influenced by any errors in our data. One other thing we should note is if you transform the data, usually that transformation transforms the median. So for example, if we were collecting data on income, quite often we want to look at the log of the income, and the median of the log income is just the log of the median income, because the log function does not change the order of the data values. So the log of the middle value is the middle value of the log values. But this isn't true for the mean. Okay? So, we will talk a little bit more about why we want to use the mean later on, as you will see when we come to statistical tests. So now we're going to look at numerical summaries for the spread or deviation of a distribution. So first of all, we need to introduce the variance. So the variance is the average square distance of the data values from the mean. So this seems more complicated, but gives a simpler theory. In fact, you might say, why don't we just use the average distance of the data values from the mean? Well, the problem is that the average distance of the data values from the mean is 0, because some of them are positive distance from the mean and some are negative. So in fact, on average, the non-square distance, so the average distance is 0. We could, of course, consider the average absolute distance of data values from the mean, but it turns out that the statistical theory for the absolute distance is quite complicated. So in general, we are not going to use that. Now, The population variance we usually denote as sigma squared. So this is one form of the Greek sigma. This is the lowercase sigma, which looks a bit like a 6. So sigma squared is the population variance. And the sample variance, so the variance calculated on the sample, is what we call S squared. And the formula for the sample variance is usually written as the summation of the squared deviations of xi's from the mean divided by n. Now, if we're using the sample mean instead of the population mean, instead of dividing by n, we divide by n minus 1. Why do we do that? Because if we're using the sample mean, we have already used up one of the data points in some sense by calculating the sample mean. So in other words, we cannot calculate a sample variance if we only have one data point. And if we only have two data points, then if you like, half the information has already been used up in calculating the mean. So we in effect only have that second data point telling us something about the variability. Okay, so the problem with the variance is that it's no longer on the same scale as the original data value. So if we were measuring on centimeters, as we talked about earlier, the variance is on the scale of centimeters squared. So in order to convert the spread or deviation measure back to the original scale, we often use the standard deviation, which is the square root of the variance. So then, of course, obviously we use the Greek symbol sigma for the population standard deviation and S for the sample standard deviation. So the standard deviation usually is how we calculate the deviation when we're using the mean as our measure of the center of the distribution. If we're using a median, you might say, well, can we find something similar to measure the spread? And indeed, this is called the interquartile range. So the interquartile range is the distance between the lower and the upper quartile, where the quartiles are the data values that divide up the distribution into quarters in the same way that the median divides it into halves. So to get the quartiles, we use the median to divide the ordered data set up into two parts, and then we apply the same formula for that half of the data set. So the lower quartile is the median of the lower half of the data, while the upper quartile is the median of the upper half of the data. So the interquartile range is just the size of the box in our box plot. So if we go back to our box plot here, as I've said, the first vertical line is the minimum. The second vertical line is the lower quartile. The third vertical line is the median. The fourth vertical line is the upper quartile. And the fifth vertical line is the maximum. Okay? And then the interquartile range is the difference between the lower and the upper quartile. So you can see it's roughly 30 just looking at the box plot. So if we come back to here, it tells us the variance is 225. We can calculate that. The square root of 225 is the standard deviation is 15. And the interquartile range is 30.5. So the interquartile range is usually roughly twice the standard deviation. May not be exactly that, depends on the data set. Okay? So this is how we can summarize our data set. That's the end of chapter 8.